So in this video, we're going to continue looking at vectors, but this time focusing on the operations we can perform on them, and we're going to look at those operations being done both algebraically and graphically. Here we see what it means to find the sum of two different vectors. So if you are given a vector u that has its own horizontal and vertical component, and then a vector v that has its own horizontal and vertical component, then whenever you're asked to find the sum of u plus v, you basically just add those horizontal and vertical pieces separately. It's kind of like having your x and your y coordinates. You add the x's and you add the y's, and then they do not have any interaction with each other. So you should still have two different pieces to your answer. So this is the algebraic approach of adding two vectors, and down here you can see what it looks like graphically for you to draw the vectors. There are two ways to approach this. The method A is the one I'm going to be focusing on more in class, but there is this other parallelogram system as well if you prefer that setup. So for vector sum graphically, you just pick whichever vector you want because the order for addition does not matter. You can either start with v and then add u, or start with u and then add v. Basically, you just line the vectors up from head to tail, and then wherever that chain of vectors ends, going from the beginning point all the way to that final resting point is your answer for the sum of the two vectors together. Now that we've seen the rules for doing a vector sum algebraically, let's look at an example with some actual numbers plugged in. So here you can see we've been given two vectors, vector u and vector v. Each one has a horizontal piece and a vertical piece. So then the question has said, find the component form of u plus v algebraically. Well, since we have u plus v, we just need to break this down as adding the horizontal pieces, and then comma, because this other part, it's like a separate answer, then we add the vertical pieces of the vectors. So then we have 3 plus 7. And if we simplify this, negative 1 plus 4 is 3, and 3 plus 7 is 10. So this is like the idea of having two different people pushing on an object. So one has a force going in these two directions, and one has a force going in these two directions, the horizontal and vertical pieces. So if both people are pushing on the same object, the net effect of them working together is pushing the object 3 units to the right and 10 units vertically. So one common application of vector sums is seeing how forces combine and interact with each other when they're either going in opposite directions or working together in the same direction. So now we're going to look at the multiplication of vectors. Now this is a special kind of multiplication called scalar multiplication. So if you are ever given a vector that has its horizontal and vertical pieces, and if they give you a constant, a real number, which you will often hear me refer to it as a scalar, so a number like 3, you can take that 3 and multiply it by the vector by just distributing it through everything inside the vector. So your vector should have a horizontal and vertical piece. If they multiply that vector by 3, then you should have 3 times the horizontal piece and 3 times the vertical piece. It's basically just like distribution, except we don't have pluses separating our terms. We have these commas in here. Here you can see the graphical effect of a scalar multiplication of a vector. So pretend for a second that vector u is defined to do something like this, which looks like a horizontal piece of 1 and a vertical piece going up 3. Well, if you took that vector and multiplied it by the scalar 2, then it would still have the exact same slope, it would just double the length. So now instead of going right 1 up 3, it would be going right 2 up 6. It doubles everything inside. The same thing would also happen if you picked a fraction for the scalar number, like 1/2. So now instead of going right 1 up 3, it would be going right 1/2 and up 3/2. So it's cut the length in half here. And the last and probably the trickiest case to do graphically for scalar multiplications is when you have a negative number out front. Now you can see that the length of this piece and the other piece over here that I showed, they have the same length, but the difference is this negative out front. So negatives change what your starting and your ending points are for the vectors. They basically completely flip the directions, but it still keeps what appears to be the same slope for the line. So now we're going to look at an example that combines both the scalar multiplication and the vector sum operations here. So we've been given two different vectors, a vector u and a vector v, and we're being asked to find the component form of 2 times u minus v. And we're going to do this algebraically. We'll do graphically next. So just like when you're working with an equation or anything in algebra, you always want to do your multiplication first and then do your addition. This is what you learned from PEMDAS. And the same rule is being applied here. So before I try to add anything with the vectors, I actually want to do this scalar multiplication and do 2 times u. So then this vector will become -2, comma, 6. And that's just me taking the vector u, which is defined here, and multiplying everything by 2. And then this is kind of tricky here, but you might want to change this into a plus and distribute the negative sign throughout it so that it's a vector sum problem to work with instead. So if you think of this as distributing -1 or multiplying -1 by vector v, then I'm going to rewrite this as -4 and -7 for the vector. So now that we've done the multiplication part, we have 2 vectors and we're being asked to add them. So make sure you're adding only the horizontal parts together. So -2 plus -4 is -6. And then as a separate computation, the vertical pieces are 6 plus -7, which is -1. So the net effect of starting with these vectors, multiplying the first one by 2, and subtracting the second one, we end up with a vector that's saying go left 6 units and then down 1 unit. So an example of a graphical representation has been shown on the earlier slides for what scalar multiplication and vector sums look like graphically, but I just wanted to reiterate those rules and then focus on that separately as its own example. So here I'm writing out the rules that you draw the vectors lined up from head to tail. So if you have 2 vectors, one going up and right, and then another one going kind of straight to the right, it does not matter which one you pick first. So if you have your x and your y axis, you can begin with whichever you prefer, and then from your starting point, draw the vector, and once that one ends, start the next one. That's what we mean by saying head to tail. So where this one ends, the next one begins. So then I connect that piece in, and then wherever that one ends, your final resting point, you want to connect that dot to the very beginning point. So the line that goes from the origin out to the final end of the vector is the answer. That's the one that is the finished operations on the vectors you were given originally. Now you could have redrawn this one, picking the other vector first, but you would see that it ends up landing in the exact same location. And that's why I tell you that the order does not matter for how you pick the vectors. So here's our last example. It's very similar to what we did in example 4, but this time I'm asking you to do it graphically instead of algebraically. So we've been given 2 different vectors, and then we see some various operations being performed on them. There's a scalar multiplication, 2 times u, and we're going to be adding these 2 vectors together. So to start off, the order you do this in does not matter. I'm going to start with vector u. You could double those numbers and think of it as 2 comma 4, or 2u also means u plus u. So you could actually break this down as saying go right 1 and up 2 units. So that would be 1 vector u. And then again do another u, so right 1 up 2 units. So this counts as 2u. It would be the same result as if you just doubled the vector u and did it as 1 line. That would be fine as well. And then since that part's done, now I'm going to look at what vector v says to do. Vector v is saying go left 3 and down 1. So from where the last part stopped, I'm going to go left 3 units and down 1, and that's where I want this piece to end. And then if I had had 2 times v, then I would do that again. I would go left 3 more and down 1 more. Since this is the end of all of the vector operations, this is my final endpoint. So you might even want to use a different color for this, just so that it's easy to tell what your final answer is. Going from here back to the origin, and making sure to indicate with the arrow the direction that we're going in, this vector is the one that represents the answer for 2u plus v. And you could check your answer for this algebraically. That's one of the nice things about doing the graphical version, because if I did 2 times u, that would be 2 comma 4. And then if I added vector v, so there's nothing being multiplied by that one, I'm just going to leave it as is. We would add the horizontal pieces, so 2 and -3 gives you -1. and then add the vertical pieces. So 4 and -1 gives you 3. And then the answer you get from this should match what your final vector is doing. This one says to go left 1 and up 3 from the origin, and sure enough, that's what I did here. So it's nice that you can check your answer pretty quickly algebraically, even when you are asked to do the problem graphically. So that's it for the notes. Thank you guys.